Okay, so 9.2, remember from 9.1 where we're introduced to complex numbers and the four different forms of complex numbers. So we were introduced to complex numbers in this binomial form a plus bi. We learned then that we can go back and forth from binomial form to rectangular form to polar form. And then we were introduced to trig form, which was r times cosine theta plus I sine theta. So we had these these four forms of complex numbers and practiced going in between all four of them. We also learned how to multiply complex numbers last class. So we saw that if I had two complex numbers, r theta, and I wanted to multiply that by s beta, then the process of doing that is you take the two distances, so r and s, or the r value, and multiply those. So we're multiplying these two complex numbers. We multiply the r values. And then for the rotations, we actually just add those together. So this would be theta plus beta. So this is how you multiply complex numbers, and we're going to be applying that today as we find powers of complex numbers, because powers of numbers are just repeated multiplication. So we'll start with this simple example. We're going to square -1 plus I root 3. I'm just going to put the I like that out front here better. So if I square this number, I'm just multiplying it by itself. So it's -1 plus I root 3 times itself, -1 plus I root 3. Even though I just said it's easier and more simple to multiply complex numbers in polar form, it's a little bright, hold on. Okay, we can still do it in binomial form. We just distribute like we would any other two binomials. So we can multiply this out. -1 times -1. So we would have +1, -1 times I root 3. So negative I root 3. I root 3 times -1. So another negative I root 3. And then I root 3 times I root 3, which is I squared times 3. So then we can just simplify it and combine like terms. So we have 1 minus 2I root 3. And then we know I squared is -1 times 3, so that would just be -3. And then we would get our final result of 1 minus 3, so -2 minus 2I root 3. So we can find powers of complex numbers by just multiplying out their binomial form. The tricky part is when you get to higher powers of complex numbers, like -1 plus I root 3 to the 9th. We would be multiplying this out 9 times. So times -1 plus I root 3 times -1 plus I root 3, and 6 more of those, and multiplying these out would be a long and unpleasant process when they're in binomial form, which brings us to how to do this a different way. And we're going to use this multiplication in polar form to help us find powers of complex numbers. So just like I've mentioned already, while it is possible to multiply two complex numbers in binomial form, we see it being easier and faster in polar form. So when we go and find the powers, if we're given this complex number, z equals √2 plus √3 times I, we're going to find the second power of that, third, fourth, and fifth. So instead of multiplying out in binomial form, we're going to find those values by multiplying them together in polar form. So the first step in a problem like this, finding powers, is convert to polar form, which means we need r and beta. So if this, remember last class, we kind of talked about how the middle form between binomial and polar is rectangular. So if we rethink this as, oops, not right three, √2 comma √3. So this is my A, this is my B. So it would be the A and then root 3 for our b. So to find r, it's just the square root of x squared plus y squared. So the square root of 2 squared, so square root of 2 squared is just 2. Square root of 3 squared is just 3. So we get an r value that is the square root of 5. Then we just need theta. We know we can compute theta by finding inverse tangent of y over x. So we need inverse tangent of root 3 over root 2. So then we can just grab a calculator, make sure we're in degree mode, and then inverse tangent, square root of 3 divided by square root of 2. So we get our value here, it's about 50.8. Let's just make sure that's accurate because this is just a reference angle. 50.8 degrees, do we need to add 360, 180? Nothing. This ordered pair to root 2 comma root 3, since those are both positive, that would be in quadrant 1. So it does make sense that 50.8 is our exact value of theta. So again, step 1, find z in polar form. So we've done that. Z is square root of 5, we found to be r. And then theta is 50.8 degrees. All right, so now that we have got our complex number in polar form and we know how to multiply two complex numbers, we can now find z squared. So z squared, and then we'll find all of these powers of z. Z squared is just going to be z times itself. So square root of 5 comma 50.8 degrees times itself. Square root of 5 comma 50.8 degrees. So we know we're going to be taking our two r values and multiplying those together. So the square root of 5 times square root of 5 is just 5. Then we're going to take our theta, 50.8, plus 50.8. So we add those together. So 50.8 plus 50.8 gives us 101.6 degrees. So this is z squared. Straightforward. We just applied what we learned last class about multiplying these. Okay, so let's find z cubed. Z cubed is going to be the same thing, except I'm multiplying z by itself 3 times. So square root of 5, 50.8 times square root of 5, 50.8 degrees times square root of 5, 50.8 degrees. Again, even though I'm multiplying 3 complex numbers by itself now, I'm still going to be applying what we learned. Multiply the r values. This time it'll just be 3 r values and add the angles. So that means for this one, I'm going to do square root of 5 times square root of 5, which is 5, times square root of 5 again. So now our r value is 5 root 5, which was just multiplying root 5 times itself 3 times. Then we're going to take 50.8 and add 50.8 and add 50.8. So that's going to be 3 50.8s. So 50.8 times 3. Oops. We get 152.4 degrees. Okay, we continue this logic. We can save a little bit of time because I'm sure you're already starting to pick up on ways that we can streamline this and not write out all 4 of these together. So we are going to be taking square root of 5, 50.8. Now, instead of writing that out 3 more times, I'm just going to put to the 4th power, and then we'll reason through what our result will be without multiplying or writing it out 3 more times. We see from z cubed, we just took the square root of 5 and multiplied it by itself 3 times to get 5 root 5. So for z to the 4th, to get that r value, we're going to take the square root of 5 and multiply it by itself 4 times. And then, so we'll compute that in a minute. Then we've got 50.8, and here we had 50.8 plus 50.8 plus 50.8. Oops, sorry, which was 50.8 times 3, and this is square root of 5 cubed. So if it's to the fourth power, we have square root of 5 to the fourth, and then this theta value will be 50.8 times 4. So root 5 to the fourth. Well, root 5 squared is 5. So basically I have 2 of those. So that's just going to be 5 times 5, essentially. So that's going to result in 25. If you don't believe me, you can just type in square root of 5 to the fourth power. You'll get 25. Then for theta, it's just 4 times 50.8. 203.2. Okay, so z to the fifth. Now, hopefully, we are even more comfortable finding the next power of z. So we will be taking root 5 and multiplying it by itself 5 times. So that's root 5 to the fifth. And then we're going to be adding 50.8 to itself 5 times, which is 5 times 50.8. So let's jump down to the pattern. So again, this guy I mentioned, I think, Abraham de Moivre, found this pattern, got the whole theorem named after him, de Moivre's theorem, and good for him, because it's not that big of a stretch, and I feel like you guys probably picked up on the same pattern he did, but he's got a theorem named after him. So if we have some power z to the n, or some power of a complex number z, all we have to do to find the fifth power or nth power, excuse me, you just take your r value, raise it to the nth, and then whatever theta is, you just multiply theta, I'm sorry, add theta. No, yeah, add theta to itself n times, which is theta times n. Let me restate that. So we have a complex number r theta raised to the nth power. To get that result, you just raise r to the nth power. So we do multiply r by itself n times, but theta, we just add up n times, which is theta times n. So that is de Moivre's theorem, and that is how you find the power of any complex number. So if we look at this one right here, we've got z given to us in binomial form. We want to compute the ninth power of z and express that in binomial form. So we start in binomial form, we end in binomial form, but to actually find z to the ninth, we need to convert to polar. So we will find r and find theta, apply de Moivre's theorem, and then convert back. So r, so again, it's sometimes easier if we think of z in rectangular form. So that's just going to be -1 comma square root of 3. So if you didn't notice, this is the same one we started with, where I said we could do that 9 times. It wouldn't be fun. It wouldn't be pretty. But now that we have de Moivre's theorem, let's find the ninth power of that same complex number using that process. R is going to be the square root of -1 squared, which is 1, the square root of 3 squared, which is 3. We get the square root of 4. So we have a nice clean value, R value of 2. Theta is inverse tangent of root 3 over -1, which is really just the negative square root of 3. All right, so we can find the value of theta using inverse tangent, negative root 3. We get -60 degrees. So let's think about that. This ordered pair, don't forget, when you're computing theta, it's just a reference angle. We need to reason through whether or not we keep that at it to 180 or at 360. So -1√3 will be up here in quadrant 2, which means a rotation of -60 gets me to quadrant 4, which means we need to add 180. So our theta value is -60 plus 180, so 120. Okay, so we had z given to us in binomial. I'm going to rewrite it now. We have z equals 2, 120 degrees. Now, if we want to find z to the 9th, so I want the 9th power of this. Applying de Moivre's theorem, z to the n, we just raise r to the nth power. So z to the 9th is just going to be 2 to the 9th. That's going to give us our r value. Theta is going to be n, or 9 times theta. So it's just 9 times 120. So this is applying de Moivre's theorem. 2 to the 9th is our result. So 2 to the 9th, that's 512. And then 9 times 120 is 1080. So 1080 degrees. This value of theta, I'm not a huge fan of. Let's get that down to between 0 and 360. So our R value at 512, there's nothing wrong with that. We keep that. But 1080 is more than 360, but we know that it's just going to repeat. So once we get to 360, that circle just continues. Those angle values just continue to repeat. So we can subtract 360 from 1080, and 720 is the exact same spot as 1080. We can subtract 360 again, and that gets us to exactly 360, which means 1080 is just a multiple of 360, which means really 1080 is in the same exact location as 0 degrees. So that is kind of crazy. So this is actually 0 degrees as a result of that 9th power of z. The only thing is this was given to us in binomial form. Z was given in binomial form. We were asked for z to the 9th in binomial form. So we are not done yet. We just need to take this and convert it back to binomial form. Remember that middle step between doing that would be rectangular form, and then we can take it into a plus bi form. So don't forget how to compute x and y using r and theta. So again, that's x equals r cosine theta. So x equals 512 times the cosine of 0 degrees. Well, if we think of our unit circle, 0 degrees, cosine is the x coordinate. So the x coordinate here is just 512 times 1, or 512. And then y is our sine theta, so 512 times sine of 0. Sine of 0 is the y value, so 512 times 0 is 0. So this was our z to the 9, which in rectangular form is 512, comma 0. Which means in a plus bi, so binomial form, it would just be 512 plus 0i. So I'm going to write z to the 9th is 512 plus 0i, which is really just 512. Okay, so quick recap there. To find powers of binomial, powers of complex number, first convert to polar. So we did that. We raised it to the 9th by raising r to the 9th and multiplying theta by 9. We got our results, then need to convert back into binomial using those conversion processes. X equals r cosine theta and y equals r sine theta. Okay, let's practice one more time right here. So if you're watching the video, I would definitely encourage you to pause, work through this on your own. If you get stuck, then use the video, but hopefully you guys can try this on your own. If not, go ahead and follow along with me. So I want to find, if this is z, this is our complex number, I want to find z to the 11th. Again, I need to put that in polar form first. A nice middle step there is putting it in rectangular form. So this would be 1/2 comma √3/2. And then to find r and theta, we do what we always do. All right, so r equals the square root of x squared, so 1/2 squared, which is 1/4, plus y squared. So if I'm squaring √3, that's just 3, squaring 2. So at first you might be nervous because we're working with fractions, but it actually works out pretty nicely. 1/4 plus 3/4 is 4/4, and we end up with an r value of just 1. Then we compute theta, inverse tangent of y over x. So √3/2 divided by 1/2. Ooh. So that would be the same as inverse tangent of √3/2 times 2/1. So really we just have inverse tangent of the square root of 3. Grab your calculator. And we get 60 degrees. Again, this is just our reference angle, so we want to make sure that that makes sense with respect to where this is based on x and y. X and y are both positive, so that means it's going to be up here in quadrant 1. So a theta value of 60 makes perfect sense. So we have our r, which is just 1. We have our theta. So we are computing z to the 11th. So if we rewrite z in polar form, 1 comma 60 degrees to the 11th power. So the 11th power of this, we're going to take, applying de Moivre's theorem, 1 to the 11th, and then we're going to take 60 degrees and just multiply it by 11. And that's going to give us, obviously, just 1. 60 times 11, that is 660 degrees. So we've computed z to the 11th. Let's simplify that a little bit, just like before with the 1080 degrees. 660 degrees is past 360. So I want to get this back down. So if we just do 660 minus 360, then we just get our value between 0 and 360. So we get 300 for that. So here we have z to the 11th. The only thing is, when you are given a complex number in binomial form and asked to compute a power of that, you need to put it back in binomial form. So you guys will be converting to polar and then back to binomial over and over and over. So you will get very good at doing that pretty quickly. So back to x's and y's, and then we can put that in binomial form. So x is r cosine theta. So 1 times the cosine of 300. This is an exact unit circle value. The cosine of 300, this is 360. 300 is here. Cosine there is 1/2. So that's 1 times 1/2. So the x coordinate is 1/2. The y coordinate would be 1 times the sine of 300. The sine right here at 300 is negative √3/2. So this is 1 times negative √3/2. So that means we have our rectangular coordinates of our, I'm sorry, z to the 11th. So it'd be 1/2, comma, negative √3/2, and then back to binomial. And we finally have z to the 11th in binomial form. So that would be a plus bi, so 1/2 minus √3/2i. So there we have z to the 11th. Given z in binomial, convert to polar, apply de Moivre's theorem to land here, and then back into rectangular, finding x and y. And then that final step of rewriting those X and Y values as A plus BI. So that is it with finding powers. Now we're going to take a look at all of the powers visually, geometrically, when we take powers of a complex number. I really love this, and you guys will see why, because it's pretty cool. Okay, we're going to use Demoivre's theorem to compute all of, now this one's already in polar, so that's a good sign, but we're going to find all of the powers z to the first through z to the ninth. This is going to seem weird, but I'm actually going to start with z to the 0th. So that means, imagine raising this to the nth. So 1.1 to the 0th, anything raised to the 0th is 1. But then if I'm raising this to the 0th, that means I'm multiplying theta by 0. So z to the 0th is just the 0.10. I'm actually going to stop. I'm going to scale this by half. So this would be 1, this would be 1.5, and this would be 2. So go ahead and scale that polar axis here by halves. And then we've got this 0.10. So this is a starting point. We're going to plot each of these powers of z. So z to the first, we were given z to the first, just z. So z to the first is 1.1 comma pi thirds. So let's graph that. This is pi over 3, by the way. This is 2 pi thirds. Okay. So pi thirds, 1.1. So again, 1 is two of these dashes. So 1.1 in the direction of pi thirds, that's just going to be slightly past 1. Now we're going to find z squared. So that means I'm going to take 1.1 and square it, and then take pi thirds and multiply it by 2. So 2 pi thirds. So let's see the result there. That's going to be 1.1 squared, 1.21, comma, 2 pi thirds. So that is 2 pi thirds is here, and then 1.21. So here's 1, 1.5 is this next line. So 1.21 is going to be about right there. And we continue with z cubed. So my r is just going to be 1.1 cubed. So that's about 1.3. And then I'm going to be multiplying, I'm going to highlight this. This is our original z, kind of going back here and raising it to the nth power every time. So that would be 1.1 cubed is 1.3. And then pi thirds times 3, which is actually just pi. So this gives us z cubed, pi is right here. So 1.3, 1 is here, 1.5 is here. 1.3 would be just slightly more than in the middle. Let's do z to the fourth. Again, for the r value z to the fourth, we're just doing 1.1 raised to the fourth, about 1.46. And this will be pi thirds times 4, so just 4 pi thirds. So 4 pi thirds is right here. And then we're going out 1.46. So there's 1. Here's 1.5. So 1.46 is just under that. Z to the fifth. We're going to raise 1.1 to the fifth. We get 1.61. 4, and then, sorry, not 4. Pi thirds times 5 is just 5 pi thirds. And then 5 pi thirds, if we go graph that, is right here. And we're going out 1.6. So there's a half, 1, 1.5. So 0.6 would just be past, slightly past 1.5. A few more to go. z to the 6th. We're going to raise 1.1 to the 6th, 1.77. And then pi thirds times 6, which is just 2 pi back here. And our R value is 1.77. So here's 1.5, 1.77, a bit slightly past the middle of those two. Couple more, and by now you might start to see what's going on here. Z to the 7th. I'm just going to give you these values. 1.1 to the 7th is 1.95. I'm actually going to work through this one. Then I'm going to do 7 pi thirds. So 7 pi thirds obviously isn't on our unit circle, but if you think about 7 pi thirds, that's really 6 pi thirds plus one more pi third. 6 pi thirds is 2 pi. So that means we're just one past that. So we are repeating angle values. So this is actually 1.95 in the same direction as pi thirds. So 1, 1.5, 2 is here. So right under it. Using that same logic, we would get z to the 8th and z to the 9th. So I'm just going to give you z to the 8th. Actually, just give you, we'll stop after z to the 8th, 2.14. And then 8 pi thirds would be the next one. But again, that's 2 pi thirds past 6 pi thirds. So that would be right here. And then we're going out 2.14. So there's 1, there's 2, 2.14, about right there. So if we look at these points, if they're just graphed like this, at first glance, doesn't seem like anything special. But what's awesome is if we go back to our first plotted point, which was z to the 0th, and then connect these points along the way in the order of their powers, we see that we have formed a spiral. So this spiral was formed by taking powers of z, our complex number, and it formed a logarithmic spiral. I know this one probably looks more like an Archimedean spiral, but this actually is an exponential growth, as we can see, because we're raising these two powers. This one's just growing a little more slowly. And that's intentional because R is 1.1. So powers of 1.1, that's going to grow a little more slowly so we can see that. So this last one is we are going to prove that powers of this complex number lie on this logarithmic spiral. This problem usually, people struggle with these problems. It's kind of like a puzzle. Do not overthink it. It's really, with a little bit of practice, you will be able to do this and make sense of it. Put a little asterisk so that when you get to the homework problem that's similar to this, you can come back and try to make sense of that. So we want to prove, which means show, convince the reader that all of the powers of this number are on the equation, on this logarithmic spiral given by this equation. This is actually, while it seems intimidating, it's basic substitution. So if this number 1.1 comma pi thirds, we want to show that integral powers, that just means integer powers, so raised to the nth, we want to show the result of that is this equation, R. To do that, this is our R value, 1.1. So, and this is our theta value. So already we have R equals 1.1, but I'm going to rewrite this. So we know that when we are taking 1.1 comma pi thirds to the n, let's keep green for now. We know that the result of that is we're going to be raising 1.1 to the n. And then we're just multiplying pi thirds times n. So that's just going to be pi times n thirds. So all I've done right now is apply Demoivre's theorem. We've got powers of this complex number, so raised to the nth. I'm just applying de Moivre's theorem here. And now I want to show that the result is this equation. So I said back here that this is R. We know that R equals 1.1 to the n. Well, we are almost done showing that this gives us the equation R equals 1.1 to the 3 theta over pi. R equals 1.1 to the n. But I want this n to look like 3 theta over pi. But we know that this is theta. Pi n over 3 is our theta value. So theta equals pi n over 3. So all I need to do here is rewrite this equation in terms of n. So I want to solve for n here and then just substitute it in. The result is going to go in right here. So I'm solving for n here. I would first multiply by 3. So that I end up with 3 theta equals pi n. And then just divide by pi to get n by itself. So now we have n equals 3 theta over pi. So now I can just replace that right here. And we have shown that R equals 1.1 raised to the n, which we solved for, and rewriting as 3 theta over pi. So I'm going to just recap that really quick because people tend to get lost here. Here are in green right here, 1.1 comma pi thirds to the n. Applied de Moivre's theorem here. And now our R value is 1.1 to the n. That's kind of our starting point for our equation. R equals 1.1 to the n. This almost looks like the equation we were trying to prove existed, except it's to the nth power, not 3 theta over pi. But we also have our theta value right here. So if theta is 3n over pi, then we can solve that, rearrange that equation for n, and substitute it back in. And then we end up with this equation of a logarithmic spiral. So all of these powers form the logarithmic spiral given by that equation. So that is it for powers of complex numbers. Again, you'll want to come back to this for one of your homework problems, just if you need to make sense of that again. That is it for today. Next class, we've done powers now. So next class, we'll be doing roots of complex numbers, which is a little more involved, but I will save that for class. Okay, see you then.